Gentlemen, here we go with part 2 for our properties of functions. And as you can see, this is, I think, the third page of the section 1.2 note sheet. And the first concept we're going to talk about is pretty basic: increasing, decreasing, or constant, and how a function can have these characteristics. Strictly speaking, a function is increasing on an interval if for any 2 points on the interval a positive change in x, meaning we're moving to the right, results in a positive change in f of x, meaning the y values. So that basically says as you move to the right, you're heading up, or you're heading up as you move to the right. So the graph might look something like this. Let's say at x equals 0, we have a y value of 1, and we're moving up, and maybe we kind of turn down a little bit, then we move up a little bit more, and we finish off at the point 3, 5. So we would say this function is increasing on the interval from 0 to 3. Now, it might be tempting to say it's increasing from 1 to 5, but those are talking about the y values. We're always going to be concerned about what x values create or make the function increase, and those x values are 0 to 3. And let's take our function a little further, and let's say, okay, for this next section of the function, it is now going to decrease. And that means on any 2 points in the interval, a positive change in x results in a negative change in y, or a negative change in f of x. So let's say this thing goes down and then settles down here. So let's say that point is 5, 2. And this one back here, of course, is 3, 5. So now you can see that our interval that we were decreasing was this portion here from 3 to 5. So we might say we are decreasing from 3 to 5. You may notice that I'm using soft brackets or parentheses on these. That's because right, for example, at this local maximum, which we'll talk about in a little while, the function's neither really increasing nor decreasing. It's kind of reached the top of the mountain. So I always use just soft brackets on these intervals. I would not include the 3 as part of that interval where it's increasing. And we'll just use that as a convention. For increasing and decreasing intervals, we're just always going to use soft brackets. Now, let's take another part of this section and say for constant, that means as we move to the right, the function remains constant. So if we went across here, we might have a function that is constant on the interval from 5 to 6. And then just to show you what the notation would look like, let's say this thing for the last little portion zips off back in the positive direction and finishes off at the point 7, 5. So we could include another increasing interval from 7 to 5. So I think that's pretty straightforward. It's pretty obvious to see where a function is moving up to the right and where it's moving down to the right. You may talk about the idea, and we'll do this a lot in calculus, of this portion of the graph here where there's a positive slope, although they're changing positive slopes. It's very positive here and it's just barely positive there. And a decreasing function has a negative slope. A constant function, of course, has a 0 slope. It's making no change at all. Okay, so that'll wrap it up for increasing, decreasing, constant. As I mentioned in class today, that's a pretty straightforward idea. So I want to move on to boundedness and what that could mean. So let's talk about that for a minute. Okay, for boundedness, we're going to talk about this idea for a second. A function is bounded below if there's some number b being a constant, like 3, that is less than or equal to every number in the range of f. That means that the y values never get below a certain number. So that means that there's kind of this lower bound. This function exists entirely above or equal to this particular number. So let's get a quick little coordinate plane here, and we'll talk about what a function that's bounded below might look like. And I think as soon as I draw this one, you're going to say, ah, yeah, this is certainly a function that's bounded below. So here is, let's say this is something like f of x is x squared plus 1. I think some of you might know that that's going to push this thing up 1 and look something like that. So here's a function whose all of its y values, all these y values up here, are greater than or equal to 1. And so 1 would be considered a lower bound for that function. Let's see if I can look at a different function, and maybe we'll use this guy here, and we'll say this function g of x is the opposite of x squared. So it's going to be a parabola that opens down. And there's a function that would be bounded above. So when we talk about a function being bounded above, that means there's some number that's greater than or equal to every number in the range, which means I'd say in this particular case 0 right there is a y value that's greater than or equal to every y value that's achieved by this function for its portion down in here. Now, this is the only place this gets a little tricky. When we talk about a function being bounded, just bounded without saying bounded above or bounded below, that means it's a function that has both kind of like it exists entirely below a certain number and entirely above a certain number. And that's something we haven't seen really yet, probably in the different types of graphs you looked at. There are plenty of them out there that do that, though. So I just drew one more little coordinate plane over here, and I could give you an example of what we call a sinusoid, the graph of like y equals sine of x, which we're going to study a lot by the fourth quarter of the year, the end of the third quarter. This is a graph that just continues to bounce up and down forever and ever and ever. And for example, if we have this function, which is, I'll call it h of x, is the sine of x. That's a function that exists entirely between 1 and -1. So we could say it's bounded above by 1 and bounded below by -1. And there you go. Because it's bounded both above and below, we would say that function is bounded. Okay, the last topic we're going to talk about, for now anyway, is going to be this idea of extrema. And by extrema we mean extremes. That's the formal plural of extremes. We're going to get maxima and minima, as a layman might say, maximums and minimums. And those are places on the graph where the y value is greater than or equal to the other y values in the area. So what do we mean by something like this? Well, we can use our graph that we were talking about with the increasing, decreasing, constant conversation from before, this graph up here. And we can think about how if there's a place where the y value is bigger or equal to the other y values in the area, I'd be looking right here. This is the highest point in this little neighborhood at x equals 3 represents a local maximum. You notice it says down here a local minimum or a local maximum is a place where the y value is greater than or equal to the y values in a certain interval. And certainly all the way from x equals 0, where we're coming up here, and we go all the way up to x equals 3, we reach this high point, then we start coming down, and we come down, we hang out down here for a while, and then we come back up, and it's finally equaled again when x is 7. But even if it went higher over here, even if this graph went up, much higher later on, let's say it got all the way up to a y value of 10 way up there, this point right where y equals 5 when x is 3, this is still considered a local minimum because he's the biggest guy in his neighborhood. Now, a local minimum, I'm sorry, I think I said that might have been a local minimum. That's a local maximum up there. A local minimum would be these guys down here. Any one of these points between x equals 5 and x equals 6 would be considered a local minimum because they are less than or equal to the guys to their left and their right. So any y value right along here, it looks like y equals 2, those y values would represent minimums, and they occur from x's anywhere from 5 out to 6. Now, if you talk about something being an absolute minimum or an absolute maximum, that's when it's the highest that the function ever gets or the lowest that the function ever gets. So if our function here is only defined, let's say this is 10 here and 0 here, if our function is only defined between 0 and 10, we could talk about an absolute min here at x equals 0 when y equals 1, and an absolute max up here at x equals 10 when y equals 10. Those would represent absolute max because he's bigger than everybody else, not just in his neighborhood. And this is an absolute min because he's smaller than everybody else in his neighborhood. And that's all there is for absolute mins and maxes. Okay, so you can see now that we've zoomed out a little bit because I want to get this last conversation a little bit about symmetry and the definition of even and odd functions. This is a big one. It's going to play a fairly significant role in the rest of your math career. Symmetry of graph is just what it sounds. You guys probably all know what it means to be symmetric, kind of the same on one side as it is on the other. And I'll take a look at, I think I've even mentioned the phrase symmetry when we've talked about a basic parabola. And I think you can see that there's sort of a symmetry going on here, that everything that happens over here on the right side also happens over here on the left side. And so this would be a graph that's would be referred to as symmetric about the y-axis. If you consider the y-axis being, right down here where the vertical line is right there, you could basically take this graph and flip it over to the other side and it would fall right onto itself. That's what it means to have vertical symmetry across the y-axis. Now, there are some other graphs that have a different type of symmetry. And it's not. You might think, well, it's going to be symmetry across the x-axis. Well, I think, that's not going to happen, because if a function's symmetric across the x-axis, that means the same thing happens up here that would happen down there. And guess what? We've just violated the vertical line test, because we'd have 2 points lined up with each other in a vertical line. So that ain't going to happen. But there are plenty of graphs that look like this, and we saw one of these today in class. It was x cubed. And now we've got a situation where, let's say we've got the point 1, 1, and then down here in the lower left we have -1, -1. Okay? So in this scenario, we have what's called rotational symmetry, which means we could take this thing and rotate it 180 degrees about the origin, rotate it right around the origin, would be like a fan blade, and it would fall onto itself. Okay, that's called rotational symmetry about the origin. Those are the two that we're going to talk about: vertical symmetry across the y-axis and rotational symmetry about the origin. Now, you might have noticed, I didn't put any points over here, but let's say we had the point 1, 1, and over here we have the point -1, 1. And here, that is the key to vertical symmetry, where we have two x values, both its positive version and its negative version, for example 1 and -1, that result in exactly the same y value. And that would happen with every x. If you had x equals 2 and got 4, over here you'd have x equals -2 and it would equal 4. So what you're seeing in this notation is if f of the opposite of x turns out to be the same as f of x for every number, that means that function is going to be what's called an even function, and it's going to have this vertical symmetry across the y-axis. Now, a lot of times students say, oh, well, f of -2, again, let's remind everybody this is the function x squared. F of -2 would be 4, and then f of 2 would be 4. So it goes, oh, well, there you go, it's an even function. It works for 2 and -2. Well, that's not enough. It's not enough just to say, oh, it works for 2 and -2, therefore it's an even function. What you have to do is demonstrate it in the kind of the general case. So in this case, f of the opposite of x would be the opposite of x getting squared. That's what it means. It means you're plugging in the opposite of x instead of x. And of course, if you simplify that, you're going to have two negative signs, and it's going to simplify to x squared, which of course is equal to f of x. So for all x's, this is true. Doesn't matter whether your number is positive, negative, whatever. So therefore, there's a definition of an even function. Now, you may have noticed, oh, that's because it's an even power. We've got x squared, so it takes it to an even power, so it strips the sign off, and that's why it's going to have this property of being vertically symmetric about the y-axis. Well, that's true. An even power can do that, but there are other functions that have no powers. For example, we're going to study cosine of x later this year, which doesn't have a power on it, but that's an even function. Absolute value of x doesn't have an even power on it. That's an even function. So don't be tempted just to say, well, the power is even, therefore it's an even function. Now, these functions that have this rotational symmetry that we see down here with the blue guy, that is a situation where when you plug in the opposite of x, you get exactly the opposite of what you get when you plug in x. So that's what I mean when we say f of -1, as you can see from this point down here, was -1, which is, of course, is the exact opposite of what f of 1 was, because the opposite of f of 1 was the opposite of 1, the opposite of that number right there. So that means we're going to have what's called an odd function. And again, to demonstrate that, I would say, well, let's look at what f of the opposite of x would look like if the function was, for example, x cubed. That would be the opposite of x getting cubed. And of course, if you simplify that, you're going to have 3 negative signs. So it would simplify to the opposite of x cubed. So you might say this is the opposite of x being cubed, the opposite of x being cubed, as opposed to the opposite of x cubed. Either way, they're equivalent, and that, of course, is equal to the opposite of what f of x was, which, of course, is the opposite of x cubed. So these guys being equal means that guy's an odd function. Now, you see that, and you go, okay, well, function's either even or odd. Well, that's another mistake, because there are plenty of functions that are neither even nor odd. So since I just told you that there are some functions that are neither even nor odd, I thought I might give you a little sample of that. So let's say we've got a function that's x squared plus x plus 1. Now, in order to test whether something's even or odd, it all starts with trying f of the opposite of x and see what that looks like. And generally, guys, remember, I think we all know that if you said f of 3, a 3 would go everywhere there's an x. So you would have 3 squared plus 3 plus 1. Of course, that's 9 plus 3 is 12, 13. You get 13. So what does it mean to have f of the opposite of x? It means everywhere there's an x, everywhere we've got an x, it's going to get replaced with, instead of like a 3, it's going to get replaced with the opposite of x. So let's take a look at that. We're going to take the opposite of x and square it, and add the opposite of x, and then add 1. And now we simplify. And this, of course, when you square the opposite of x, you're going to get x squared, because we've got 2 negative signs. This guy is just going to become minus x, and then the plus 1 was basically unchanged. So f of the opposite of x is x squared minus x plus 1. Now, our mission is to determine if this thing's even or odd. Well, if it was even, this would be equal to f of x. So let's see if that holds true. I'll put a question mark there. And f of x, of course, is x squared plus x plus 1. So I ask you, is x squared minus x plus 1 exactly the same as x squared plus x plus 1? And I think you can see, no. So it is not an even function, because f of the opposite of x is not equal to f of x. So here we go, and we're going to see if it's odd. Well, if it's odd, we also want to start with f of the opposite of x, which turned out to be x squared minus x plus 1. And now we're going to compare it to the opposite of f of x. Well, that means we're taking the opposite of f of x, which is x squared plus x plus 1. Simplify that right side, you're going to get the opposite of x squared minus x minus 1. And if you look at the left side, we have x squared minus x plus 1. Lots of stuff not the same here. We had an opposite of x on one side, opposite of x squared on one side, regular x squared on this side. These guys are actually the same, but I got a plus 1 here and a minus 1 there. Clearly not equal, so this is no, you are not odd either. So, gentlemen, if you're ever asked to determine whether a function's even or odd, this is the test you do. Everywhere there's an x, replace it with the opposite of x and simplify like we did there, and then compare that resulting function to both f of x to see if it's even, and compare it to the opposite of f of x to see if it's odd. If it's not equal to either one, then it's neither even nor odd. All right, there you go. That's it for this Properties of Functions Part 2 with covering, let's see, we started with increasing, decreasing constant. We went on to boundedness. We went on to extrema, maxes and mins, and then we finished off with even, odd, and the symmetries that result. See you tomorrow.